Hello, welcome to an introduction to formal logic. My name is Mark Thorsby, and in this video, what I want to do is I want to talk a little bit about philosophical logic, and I want to give you a brief tour of the development of logic, noting some of the important theoretical advancements that have occurred within the branch of logic. And before I sort of begin the video, I guess let me say a little bit of word about why I wanted to do this video. A lot of times when we take logic courses or when we teach logic courses, for those of us that do, we tend to simply teach the mechanical techniques regarding the logical system we're working on. So in this introduction to logic course that we've been doing here, we've looked at three different types of logical systems. We've looked at categorical logic, propositional logic, and predicate logic. And we've also looked at informal logic. These are the three formal systems of logic. And keep in mind, each one of these has its own name that could be different. So categorical logic, what we've been calling categorical logic, is also well known as syllogistic logic. Propositional logic, that's what we've been calling it, is also known as sentential logic. And then predicate logic, which is what we're going to be learning about next here. Predicate logic is also referred to as first order logic. So these all have different names, but each of these systems constitute major developments within logic overall. But one of the things I realize is that when we teach this course, we tend to simply just teach the mechanics, the way to calculate validity, either in propositional context or with quantifiers in categorical logic, and the same thing in both predicate logic as well. We may tend to teach the mechanics, but a lot of times what we're missing, or what I think students are missing in these introduction courses, is a sense of the philosophical problems that are at stake in the development of logic. Because ultimately, all of these logical systems that we've been learning about have all been developed ultimately by philosophers who are attempting to resolve or explain certain philosophical problems that relate to logic. And so what I want to do today is sort of take you through a tour of some of the important moments within each of these philosophical systems and see if, so that way you can get a sense that all of this stuff we've been doing in our course actually has fairly substantial philosophical problems and questions undergirding the whole thing. And many of these sort of elemental questions, we might call them, these questions are so fundamental and so foundational that in many ways there is no wrong or right answer at this point. Nothing's been proven either way. So we have sort of a fascinating tie-in here. I remember when I first took logic, and I remember the course lacked more than anything was sort of a narrative, sort of context to see what was happening. And the irony is the way we teach logic in categorical, propositional, and then predicate calculus, these forms of logic are ultimately... So let's just get right to it here. Sorry, I was sort of interrupted there by my neighbor. So let's sort of talk here about categorical logic. And you're going to see here that really the language of categorical logic doesn't... It's applicable ultimately in terms of what we're going to be talking about. But you're going to see that we're going to be talking about issues that transcend simply categorical logic. But to sort of start off with categorical logic, we can really talk about it in the classic sense, because ultimately categorical logic was developed fundamentally really initially by Aristotle and then developed further by later philosophers, especially in the medieval period. But the sort of nuts and bolts of categorical logic is developed by Aristotle as syllogistic logic. So all of the sort of nomenclature that we have for categorical logic was much of it was developed in the Middle Ages, and it's completely foreign. So you won't see Aristotle talking about the same issues in his works ultimately with the way we've been talking about it in the context of our course of doing the form and the mood and all that sort of stuff. So, but before we sort of get to Aristotle, I want to start off here with pre-Platonic logic, because ultimately we can't discount Plato in terms of his influence in philosophy is so large that we can't we can't ultimately exclude him from the history of logic, but we'll see that really he doesn't develop anything nearly to the formal degree that's necessary. But before Plato, even, we have the pre-Socratic philosophers, or what I'm calling pre-Platonic logic. And of course, this is by no means meant to be an exhaustive sort of summary of the development of logic. So I want you to know that I'm just giving you sort of the bird's eye view of the development of logic, or if you will, the ideas within the history of philosophical logic that are hopefully accessible to anyone watching the video. So this is not, you don't have to be an expert to understand hopefully what we're going to be talking about today. So first out is Heraclitus. Heraclitus, he's famous for arguing, or at least he's frequently attributed as having said that you can never step into the same river twice. And we won't go into the analysis of that or the correct translation of it, but we can say that one of the things that was fundamentally first articulated by Heraclitus was the notion of binary opposition. The idea that some concepts are binaries to other concepts. For instance, now in an unrefined sense, Heraclitus would say things like, cold is the binary opposite of hot, for instance, or justice is the binary opposite of injustice, I'm sorry. Right. So Heraclitus ultimately, I mean, he tried to create a whole metaphysical system out of binary oppositions where how are the opposites somehow able to be linked together? How are they related together? He argued through some sort of harmony. Interestingly enough, ultimately Leibniz would actually take a similar idea in his monadology. But so we get Heraclitus as sort of the recognition that there's binary opposites. And Pythagoras, of course, most people know Pythagoras because of the Pythagorean theorem, and they're aware that he's a famous mathematician. But one of the things that he's important for having advanced is geometric proofs, and demonstrating how to conduct geometric proofs. Of course, the proof to the Pythagorean theorem is probably the most famous of all of his geometric proofs, but there are others, and ultimately, this idea that you can prove that something's the case that is not easily recognizable as the case actually proves quite important, because it ultimately shows that through symbolization, we're able to prove things about big, huge material things that exist in the world, right? So we get Pythagoras here. And I think even Thales, I didn't put Thales on here, but he's probably an earlier pre-Socratic, but he's often attributed as having been able to measure the pyramids, because ultimately he was able to recognize that the ratio at a certain time of day in terms of your shadow could be measured, and that would be identical to your length. And so that's what he did. Now, whether or not that's all true, no one really knows. But even Thales, for instance, is a great example of using mathematics in application. Of course, the Egyptians initially developed mathematics, but Pythagoras here is able to articulate a proofing system of some sort, rudimentary sense. Now, the first written work in logic is actually called the Dissoi Logoi, and it's a fragment from the 4th and 5th century BC. And here's a sort of example of what the book would look like if you wanted to read it. And this fragment ultimately concerns the possibility of falsehood and contradictions. And what's really important for us is that it's the first written work in which it's clear that someone is arguing that contradictions are possible in discourse, such that if an initiate says, I am an initiate says, I am not an initiate, right? You can see the second case ultimately is a contradictory case. And so it represents the idea that we can talk about contradictions in language versus contradictions in reality. And I shouldn't say it's not a philosophical treatise. It really is very sort of simple, and probably for most of us it would be hard to, if we read it, we may not understand the full implications of the extension of this book in terms of the development of logic. But nevertheless, it's considered an important sort of work. Because ultimately contradiction, as you'll know from the rest of our course, has proven to be extraordinarily critical and crucial in terms of isolating or articulating the various laws of logical relations. So, in terms of validity in particular, right? Okay, so let's move over here to Platonic logic. So the question is about Plato. So Plato really doesn't have a huge place within the development of logic. But of course, he is notable for really sort of two different things. The first thing that he's well known for is what we might call problems of definition, where in many ways the Platonic discourses and treatises and the dialogues, whether we're talking about the Republic or the Meno or the Phaedo or whatever other dialogue you were talking about, most of these dialogues operate by trying to isolate the definition of something. Now, for Plato doesn't make the distinction, well, I have to be a little bit careful here because I think he does, but not in the same way that we would make the distinction in modern philosophy. But I think he's aware of it. But ultimately, he doesn't want to know just the definition of our words. He wants to know the definition of things in the world, metaphysically. And so it's always, his discourses are always organized around the investigation of an essence of some sort of thing, right? And then how does Plato proceed in terms of trying to determine what a definition of something is? And when I say definition, I mean it in a metaphysical sense. So not just what the word means, like you read in Webster's dictionary, but the definition being precisely what is essential about the said thing such that it is the said thing. So, for instance, here's an example. I've got a coffee cup in my hand here, right? So you can ask yourself, what's the essence of a coffee cup? What makes a coffee cup, as opposed to a water cup or some other sort of cup, or some other object, non-cups? And Plato ultimately wanted to articulate the essence, and he ultimately did it through his theory of the forms. And I won't go through all that now. You can watch one of my other videos if you're interested, where I lay out a sort of summary or overview of Plato's theory of the forms. But so Plato proceeds by trying to isolate these essences, and he does it through what's called the method of division. And I sort of have an example here for you. Let me zoom in here. Right. So for example, imagine, for instance, if we wanted to know what a Labrador, I just wrote lab, but a Labrador dog is. Well, you can see that animals, if we have a category of animals, animals are either mammals or reptiles. If they're mammals, well, there's different types of mammals. There's dogs, there's horses, there's cats, and so on and so forth, right? And then one of those many types of dogs is a lab. Of course, there's other types of dogs. There's poodles and so on and so forth, right? But you can see what we're doing here is we're taking categories and splicing them apart, ultimately to determine what the essence of something is in relation to the essence of another thing, right? So the essence of a lab is such that it has a species relationship to the genus of dog. Now, the species-genus distinction, it actually is the distinction, is actually developed by Aristotle, but ultimately Plato recognizes the exact same logical relationship. So the difference, though, is, for instance, here I just gave the method of division example using animals because it's simple, but you can see, for instance, in the Republic, the method of division centers on the question of justice. And there, through a complex set of analogies, Plato ultimately tries to divide up the component parts of justice in order to then understand ultimately what justice is in its totality, and of course, notably, whether or not we live just lives or we live in just societies and so on and so forth, right? But this is essentially the sort of logical process that ultimately Plato employs. Now, Aristotle's where things get a lot more formal, and I think you see major advances in terms of a finer articulation of what's going on in logic. And of course, you see the development of categorical logic fundamentally as we know it, at least in terms of its principles, axioms, and so forth. So I can't go over everything that Aristotle talks about. I'd never get through this video. So I'm just going to give you here some of the touchstone points. I'm not going to review categorical logic because you can watch the categorical logic videos to do that. But we can start by saying that Aristotle first distinguishes two types of reasoning. Let me zoom up here. On the one hand, we have apodictic reasoning. Now, for Aristotle, apodictic reasoning is a type of reasoning that a teacher does. That's where, remember, whenever you have a premise, you can always have the contradiction of that premise, right? Those two things cannot be the same. Those two things can't be true at the same time. So the apodictic form of reasoning takes one side of that two contradictory premises and then it tries to demonstrate the truthhood of this one versus the other one. So this is what teachers do, for instance, when a teacher is trying to teach you about Aristotle, for instance, or that's not a good example, but let's say when a teacher is trying to teach you about science, let's say biology, and you're learning about animals, right? A teacher, right, will try to use reasoning to show you why you should agree with what the scientific consensus is, or what something like this. Whereas the second type of reasoning is the type of reasoning that's largely employed in Plato, which is dialectical reasoning. And that's the analysis of both sides of a contradictory pair of premises. That is the sort of reasoning that a detective makes. So for instance, the teacher already knows what they think, and they're going to prove what they think using demonstration. Dialectical reasoning seeks to evaluate whether or not dialectical reasoning doesn't proceed with the assumption that we know the answer. And so the argument is to try to figure out which of the two premises that are contraries of each other is going to be true. So for instance, a detective, right, tries to figure out both. Let's say a detective analyzes both why someone could be guilty and also why someone could be innocent. So that's a sort of dialectical form of reasoning. Now, clearly there's more sophisticated definitions we could give there, but in general at this point, that's going to be sufficient for understanding the basic difference that Aristotle sees in terms of types of reasoning. Now, Plato's stuff dealt primarily with dialectic, but we're going to see that much of Aristotle's work involves the analysis of optodictic reasoning. Now, but we should be clear here is that syllogisms are used in both. So the other thing is Aristotle makes a distinction in terms of truth. So on the one hand, we talk about something being true. Something can either be true by necessity or it can be true by contingency. So necessity would be, for instance, if I say a squared plus b squared equals c squared, right? That's the Pythagorean theorem. That statement is true by necessity. That is, there's no other way to understand. Mathematically, that has been proven multiple times in multiple ways such that that claim is always true, right? So we have the idea of necessary truths. By contrast, we have contingent truths as well. So a contingent truth is when I say, for instance, it's raining outside. Well, it's either true or it's false based upon whether or not that statement corresponds to some sort of state of affairs, right? And that's purely contingent on those state of affairs, right? So if I say it's raining outside, there's nothing in that statement itself that makes it necessarily true. Whereas if I make a geometric proof of something like the Pythagorean theorem, I seem to be rubbing up against things that are true out of necessity. And so there's these two types of truth. And you're going to see ultimately for Aristotle, the strongest is to seek truth by necessity, not contingency. Though he doesn't deny by contingency, right? Observation is a critical factor in terms of developing our knowledge of the world and what we consider to be true in the world, right? Now, notice to some extent, this is not the same thing as, but there is a sort of relationship here where you can see a sort of proto-distinction here between deductive and inductive reasoning. But it's not fully developed yet, so we got to be a little bit careful about that. So the next sort of major things here worth mentioning about Aristotle is first, and I've mentioned these in the class before multiple times, but the first is the law of non-contradiction. So the law of non-contradiction, I gave you an example here from the Metaphysics book 4 here, where Aristotle says it is impossible for the same thing to belong and not to belong at the same time to the same thing and in the same respect with the appropriate qualifications. Now, we won't worry about those qualifications right now. But basically, law of non-contradiction, or the law of contradiction as it's sometimes referred, ultimately states that you cannot say that something is and is not. Something cannot both be and not be at the same time in the same way and in the same respect. Right? I can't say that I'm recording this video and I'm not recording this video. Those two statements can't be true at the same time. That would be a contradiction. And we'll see this is the fundamental law of logic, period. All logical discourse, and in fact probably, or at least the grand majority of them, not all of them, require or are premised on the law of non-contradiction. Right. Now, a similar one, and I didn't give you the Aristotelian quotation here, but is what we call the law of non-excluded middle, or the law of excluded middle, sometimes referred to. And that basically refers to the principle of bivalence. That is, propositions are either true or false. They can't be in between. There's no middle ground, if you were. Right? So if I say it's raining outside, that's a proposition, and it's a proposition because I'm making a claim about something. And if that's the case, that claim is either going to be true or false. So you can say that bivalence refers to the idea that things can either be true or false. And the law of excluded middle is essentially the principle or the axiom upon which that's based. Um, and that's really quite important. And ultimately, if that wasn't the case, and if it's not the case, then it means that there would be severe ramifications in terms of logic as well as mathematics. Okay, there's the one thing. Now, Aristotle developed really, he's famous for developing syllogistic logic, which is what we've been calling categorical logic, as well as modal logic, which is also a form of syllogistic logic, but we haven't been discussing modal logic at all. So I'm not going to talk about that in this video. But modal logic, if you read about it, refers to logic about regarding things of necessity. So just like how we've developed the traditional square of opposition, there is an opposition for modal logic, a square of opposition as well. So we're not going to go over that, but Aristotle is very, very well known for being the father of at least archaic modal logic. So, but back to syllogistic logic. What is syllogistic logic? Well, it's the analysis of syllogisms, their categories, and the necessary relations between those categories and between those statements and arguments, right? Now, I didn't really want to spend too much time going over all of the different aspects of categorical logic, since that's what our course has done already. But you can see here that ultimately syllogism essentially is a two premise, one conclusion argument with three core terms or categories or classes. And we've talked about how those are related in a whole number of ways. Now, Aristotle, it's quite remarkable because even if you don't find the categorical logic stuff extremely, you probably don't find it nearly as robust as the stuff we've been working on now in terms of predicate logic, but it's remarkable to think that Aristotle came up with all of this without any symbolization whatsoever, purely just insightful analysis. Now, but for Aristotle, the reason he wanted to develop syllogistic logic is because ultimately he thought the sciences depended upon it, right? Is that art, like, there's a classic distinction that Plato and Aristotle make here between arts and sciences. An art is where I essentially gain experience over time of something. I don't really know why what I'm doing works, but I know that it works. So you can say, for instance, someone could teach me how to cook, for instance, cook a recipe, but that's a sort of art. The science of cooking would be knowing why when you blacken something it gets the kind of taste it does, or something like this. So there's a difference between arts and sciences, and ultimately the goal of philosophy and ultimately the goal of education is to develop our knowledge in terms of science, not in terms of art, but in terms of science. And so Aristotle thought that in order to advance science, we had to be really clear about how we make our arguments and how those arguments can be related to each other and extended and applied to other modes of discourse. So science needs to know what the basic laws of logic are, and so he developed the syllogism and his analysis of the syllogism accordingly. Eventually, he developed this into a metaphysical theory here, which we call Aristotle's doctrine of the categories. And I'm not going to sort of go through this because ultimately to fully understand it would require us to sort of go back and to sort of start fresh and look at Aristotle's work. And we just don't have time to do that. But this is from Aristotle, right? Any being, according to Aristotle, is either said of another, that is, when you're relating two categories. So a category refers to a being, a set of beings, right? So any being is either said of another, right? Right? And we're talking about universals, or it's not said of another, it's said of particulars, right? So likewise, any being is either present in another, it's accidental, or is not present in another, it's non-accidental. So what we have here is we ultimately have four possibilities. We have accidental universals, non-accidental universals, accidental particulars, non-accidental particulars, and ultimately primary substances for him, right? Which is ultimately the goal of science, is to analyze the primary substances, right? Think, for instance, a dog is a substance, and the goal of a scientist is to understand how that substance works. But that primary substance is a non-accidental particular. So I'm not going to go through what all that means, but you can see here, this looks very, very much like what we've been working on in our course here, in terms of, we've been calling them universal affirmatives, universal negatives, and so we have a slightly different language here, and that's because ultimately we would have to unfurl the Aristotelian language here and the way he discusses it and ultimately make full sense of the doctrine of the categories. But the doctrine of the categories is quite critical because what it argues is that ultimately science is organized according to the way in which our categories are organized in logic. So this has huge ramifications in terms of Aristotelian science. Now, Aristotle eventually developed articulated what he called the 10 categories of being. And we won't go through those now, but there's a lot of different, like the time of something, the location of something, the relation of something, so on and so forth. These are the categories by which we can analyze or investigate being. And so Aristotle is developing categories and then trying to develop a categorical system for the analysis of whatever it is the science is working with. Now, logic ultimately then is a tool of science for learning about the world. And that's quite critical for Aristotle. That's how he sees the importance and the application of logic, is ultimately developing the ground rules, the mechanics for understanding clearly how a scientific argument should be structured such that we can gain knowledge. But the other really critical thing about Aristotle's philosophy here is that logic is not only the structure for our thoughts, but it actually reflects the structure of the world itself, both in terms of primary and secondary substances, and ultimately in terms of the essence of things. And by essence, we mean the same thing that ultimately Plato was seeking after in terms of his theory of the forms. So you can see here, if you'll recall a couple, at the beginning of our term here, we talked about the existential fallacy quite a bit. And you can see here, remember Aristotle, argument was that universal statements imply existence. And the reason he thought that was ultimately he believed that in an axiomatic fashion, that logic is not just in our head, right? Logic isn't a psychological feature for me understanding and having cognition of the world. No, logic refers to the laws that actually govern the relationships between actual beings. Right? And so the idea here is that that if you could over time gain knowledge of universals logically, then clearly you would gain knowledge of the world, right? So you can see here the sort of what we might say is the naive view of the existential fallacies right here based in Aristotle. And we'll talk a little bit about that in a minute, but I'm going to move forward now here into modern logic and talk quickly about Gottfried Leibniz. And Leibniz, you can see here, he has a very interesting haircut, or lack of haircut. Leibniz is a huge and critical philosopher. Interestingly enough, he probably is the most noteworthy person in terms of helping to develop propositional logic, but he doesn't have much he has historical importance as a philosopher, but most of his treatises on logic were not even discovered until 1905. So much of his work he never published. I don't think he published one book in logic when he was young, but he didn't publish other books. So almost all of the works on logic that he had and all of his developments were purely just personal. He didn't tell anyone about them. But we might say in terms of looking at logic, there's really four areas of influence, or there's four main areas that Leibniz spent his time looking at and working on. One is the syllogism, and there you can see he's basically working in the same vein of thought that the classic logicians like Aristotle were. And of course, by the time that Leibniz lived, we're talking, centuries after Aristotle, and there have been quite a few more developments in the Middle Ages and in the early Renaissance that had already pushed the discussion of syllogisms forward quite a bit. But he also spent much of his time thinking and working on the syllogism. Now, they also began working on the notion of universal calculus, and of course, Leibniz is actually typically given the attribution of developing calculus. Here we're talking about mathematical calculus. Um, he actually developed it at the same time, maybe a little bit after, but ultimately independently of Isaac Newton. Isaac Newton is usually given the credit, but Leibniz actually, that's the formal system we actually use in terms of the symbolization for doing derivatives and all that. We use the Leibnizian version. We actually don't use Newton's version, but we give Newton the credit, ironically. So I'm not sure who wins. Maybe Leibniz got the better deal. I'm not sure. But Leibniz also develops the first early parts of propositional logic. Now, we should be a little bit clear here is that ultimately his propositional logic is significantly hampered by an inability to extricate himself from the syllogism. And ultimately, that's one of the issues, is that categorical logic takes statements, premises, and then tries to analyze the relationships between the terms within those statements. That's how we have quantifiers, right? So when I say that all logicians are smart people, I'm quantifying, I'm using a quantifier, I'm saying all, and there's a logical relationship there in terms of how that plays out in terms of the actual terms. That's the distribution, if you'll recall. But you can see here in propositional logic, that's where instead of looking at quantifiers and the terms, we look at whole concepts, whole propositions. And in fact, Leibniz referred to propositional logic as a sort of concept algebra. He doesn't really use the term propositional logic per se, but ultimately he developed at least all of the fundamental principles and axioms that we've been learning in propositional logic. But ultimately he was still not quite successful. We'll show why in a minute. And finally he also did some work in modal logic, but we'll skip ahead with that. How do I get in here? Let me see if I can zoom in. Okay, yeah, so here's sort of the goal of when we're thinking about Leibnizian propositional logic or his contribution, we can say that Leibniz's goal is ultimately to state and prove the laws of concept logic. That's the idea that we don't when I do a hypothetical syllogism, right? When I say, if you go to the park, then you're going to get wet. If you get wet, then you're going to get cold. So, if you go to the park, then you're going to get cold, right? That sort of where I'm relating concepts to each other doesn't conform to the categorical form, right? So you had to develop a completely new way of doing logic. And it ultimately concerns the way in which we relate our concepts together. And Leibniz developed the rules in order to articulate this concept logic. He developed all of the rules and the laws of propositional logic. And again, he never published them at all. Not in his own lifetime. Of course, they have been published since. And so he actually went as far as to develop a symbolization for this concept algebra. It actually comes from the Notations Generales of 1683 to 85. Forgive my lack of accent there. And I have a sort of picture of it. Let's see if we can zoom in. You can take a look at. This is actually Leibniz's notes here on the concept logic. It's hard here to tell what's going on here, but I will point you out some of the things. So this X with a circle here, and he also has a negative and a plus. Here he's trying to isolate the bivalent properties of things, and I believe this is a conjunctive operator, and it's sort of a mess here to read because it's just a picture. But he ultimately went on to develop the symbolization for conjunction, disjunction, the conditionals, negation, and so he actually developed this sort of full-fledged system, but it didn't work ultimately, and he became frustrated and then abandoned the project and never really finished it. But part of the reason was because he wasn't sure how he could ultimately account for the difference in quantifiers, right? Because he wanted to merge the concept algebra with the syllogistic logic, which would be sort of a match made in heaven. You could unify these two logical systems, but he wasn't able to do it, and he never really was able to go very far on that problem here. Let's see here. Let me go back here. So here's a quote from Leibniz here. Right, he says, he writes, this is from page 75 of his treatise here. If, as I hope, I can, I'm sorry, subsection 75, not page. If, as I hope, I can conceive all propositions as terms, and hypotheticals as categoricals, and if I can treat all propositions universally, this promises a wonderful ease in my symbolism, an analysis of concepts, and will be a discovery of the greatest importance. And ultimately, you can see here he's starting to get just to what the analysis of predicate logic, but ultimately he was hampered by his symbolism. His symbolism didn't work out because he had difficulty isolating how the quantifier, how he had difficulty showing how the quantifier symbolically related to the subject versus the predicate terms within a proposition. And so he had the symbolization, he had the right idea, but he really couldn't progress too much further. And it's sort of ironic from a philosopher whose entire metaphysical system is ultimately based on trying to do just that. That is to isolate the logical relations between substances. That's what his monadology was all about. So that's a little bit about Leibniz. Of course, that's really quite cursory, but you can see here that Leibniz takes it forward here a bit. Here's where we sort of have the bad boys in the development of logic. First, John Stuart Mill and David Hume. The first thing I'll say is the thing that's important about John Stuart Mill is John Stuart Mill ultimately argued that mathematics utilizes inductive reasoning. Now, John Stuart Mill believed that our knowledge came from experience. He sort of fell under the umbrella of the British empiricist movement there, thus. And he argues that we have experience of things, of numeral things, right? Of multiplicities. So on my desk, I have two or three pens, right? And my experience is I have this experience, and then on top of that experience, I basically give abstract names. And that's what numbers are, right? So what is one thing? Well, it's when I take one thing and I give it a symbolic name, 1, right? And 2, 3, 4. But he went as far as to say, but also the logical operations between them are also inductive. So, for instance, if I say 2 plus 2 equals 4, why do I think it equals 4? Well, because in space, in the world, I take my experience of 2 pens and I take my experience of 2 other pens, and when I count them up, it's always equal to 4. So I can create symbolic operators for the numbers. I can put a squiggly line here and a plus sign here and a squiggly line there, and then I can do an equals and a for symbol. So I can sort of write a symbolization out, but what I'm ultimately symbolizing is a certain feature correlated to my experience. But guess what? Since it's inductive, that means that it's not deductive. We typically say that mathematics is deductive reasoning. That is reasoning by necessity, or at least most types of mathematics are. But you can see here, if John Stuart Mill is correct, then everything's sort of like sand through our fingertips. We sort of lose the ability to grab hold of why we should think that mathematics is objectively true. And of course, this has huge ramifications for logic, because ultimately, and it's hard to say here whether or not logic and mathematics are even different, but ultimately, the objectivity of mathematical and logical sciences is what's at stake. And here we can reference David Hume's problem of induction. And I sort of typed this up. I don't think it's probably the best analysis or the description of the problem of induction. But we can simply say this is that if our knowledge about the world is derived from contingent, particular experiences, and those experiences do not reveal the essential nature of the things that we're experiencing, right? So I can see, for instance, I can see a rainbow, but I don't really know, my experience of the rainbow doesn't give me, insight into the nature of rainbows themselves, right? The sort of physics of rainbows. Well, what that means is that my knowledge becomes essentially descriptive in nature, and it's not absolutely certain, right? That is, and the problem of induction is really more so understood with what is sometimes referred to as the black swan problem. And that's the idea that everyone in Europe believed that all swans were white, a universal statement, right? from categorical logic. They believed all swans were white until what? Until they saw black swans, right? So you can see here that you could create, based upon your experience, you have a regularity to your experience, and then we hypothesize universal principles to understand why that regularity is the way it is. But every once in a while, that regularity is interrupted, right, by some sort of extreme event. And if that occurs, that reveals that we actually don't have the universal principle down, that we actually don't have that knowledge that we think we do. Now the problem is, if mathematics is inductive and it falls prey to the problem of induction, that means that 2 plus 2 could equal 5 potentially someday in the future, an unimaginable future, but potentially nonetheless. Now, David Hume ultimately tries to get around this problem, I think, and he probably does get around it by making the distinction between matters of fact and relations of ideas. But we won't go through all of that right now. I just want you to see here that by the time we get to the British empiricist, ultimately there's a sort of kind of skepticism that's initiated regarding the efficacy of logic in mathematics in terms of whether or not it truly is a universal science. And ultimately, I think this is hinging upon on whether or not we can understand logic to be related to the world or whether or not logic is related to the mind. And we'll return to that question here in just a moment. So what are some of the major advancements after this sort of period? Well, obviously, first here is Augustus de Morgan's theorem, which by now you all know. So, De Morgan's theorem, but George Boole is really the big boy here. And then, of course, I didn't even put Venn on the list here, but we could put him down too, John Venn. But George Boole, like Frege, wanted to replace syllogistic logic with the concept algebra. And he effectively works to do just that. He also discusses, most importantly for us, the existential fallacy. And for him, he denies the universals give us this sort of, he denies the idea that universals imply existence. And maybe philosophically you can start to understand why. That is, universals can't imply existence because we can't be certain that universals have actually even been experienced, right? So for instance, imagine, this is a sort of, well, yeah, I mean, a good example of this would be think about rain dancers, right? Imagine I lived in a village, in the 5th century, and when there was drought, and I'm a farmer and I need water, I'll call in a witch doctor or a shaman or a rain dancer. They'll come out, they'll say some prayers and incantations, maybe light some incense, dance around or something, and then the rain will start to fall, right? And let's imagine that this occurs over and over and over and over again, and it occurs consistently, right? I'll start to believe, quite rationally, in fact, that the rain dancer or the shaman is actually causing the rain to fall, right? And there I think I have hold of a universal when I don't, right? So the idea here is that when you make universal claims, they don't imply existence for a very good reason, which is namely what you've done is you've postulated a universal from particular experiences, but particular experience is the only way we have knowledge of existing things. We don't have knowledge of existence at a universal level, even though we make universal claims. And so that's why Boole ultimately differentiates the existential fallacy the way he does, at least in a sort of quick, shorthand way of explaining it. And of course, Boole eventually developed Boolean algebra or Boolean operators. And this forms the basis of what we do in propositional logic, as well as in sort of simple computer object orientation logic as well. So for those of you who are watching this who do computer programming, you've been using Boolean operators potentially for years. And these were developed, though, ultimately not to make computers, not to have calculating devices, but they were developed in response to these philosophical problems we're discussing right now that I'm trying to give you a quick gloss over here. I want you to see that is that these guys are working on these problems, and these problems are not that's out of order, obviously. And these philosophers and mathematicians and logicians are working on these problems, and they're not doing it so that we can get the science for making computers. They're doing it because they ultimately want to solve or eliminate certain philosophical possibilities regarding ultimately what we're even doing in mathematics and logic. So it's pretty exciting stuff. And then, of course, it becomes hugely important in terms of its practical application. So the next sort of philosopher here, and now I'm jumping ahead near to predicate logic and I'm moving here to sort of the father of predicate logic, who is Gottlob Frege. Here's a picture of him when he's a pretty old man. Now, what was in here? And Frege is usually attributed as being the person who articulates first order logic, what we can refer to as first order logic, or predicate calculus, the way we've been referring to it in our course, right? And what's the goal? Frege has a number of different goals, but two of his basic goals is one, to establish that the laws of arithmetic are derived from the laws of logic, right? So there's a question here: is we have these logical laws, like the law of non-contradiction, and then ultimately we can come up with we can articulate logical laws in terms of formulations like De Morgan's theorem and so on and so forth, right? But the question is, what's the relationship between these things and all these other things over here that the mathematicians are doing? When I add things together, am I using the same bit of logical law that's ultimately in operation when I make a syllogistic argument, a hypothetical syllogism, for instance? And so Frege thought yes, and he wanted to prove it. And he did it, or I don't know if he did it, but he saw that was ultimately one of his goals. And the other thing was to establish the objective certainty of the laws of logic. So we should be clear that although Frege would say that we use the laws of logic in our mind when we think about things, he would not say that they just exist in the mind, right? So for Frege, mathematics and logic ultimately articulate laws of reasoning that go beyond the reasoner, right? There's almost a sort of in Frege, in his early work you see this significantly, there's almost a Platonic tendency, right? To see the laws of logic as somehow transcendental. So now, how does he do this? Now, obviously, there's lots more we could talk about. Another thing is, Frege was he's a trained mathematician, not a philosopher, but he is a philosopher. But he's working as a mathematician. Well, he did this by developing the axioms of predicate logic and also developing a symbolization schema. But before we go through that, I want to give you before we can really understand Frege here, we have to understand Cantor. And Georg Cantor is essentially a German mathematician who lives really the generation prior to Frege. And he's the inventor of set theory, or what is sometimes referred to as naive set theory. Well, let me sort of go through here and tell you a little bit about Georg Cantor, right? And ultimately, set theory refers to the language of the mathematics of infinity. Now, let's go back even further before Cantor and look at probably the most important person before Cantor to really think about the question of what exactly is infinity, right? Well, one of the things we can do in order to this is Isaac Newton. One of the things we can do to understand infinity, or to think about infinity, is to recognize that a circle is infinity, right? Infinity in terms of the infinitesimal, right? Because a circle we can define as an infinite series of points by a set radius around a single point, right? And so a circle has an infinity amount of points, right? You can keep dividing how many points are in your circle infinitely. It goes on and on and on. But the problem is, what happens if you have two circles, right? What if you have circle A, which is smaller than circle B? And what happens if we superimpose them? In fact, I've superimposed and changed the color here. So the green circle here is actually the same as color A, and the yellow circle here is color B. But you can see here, wait a second. If A is bigger than B, which it clearly is, right? Then it would seem that infinity A, I'm sorry, I wrote this down wrong. If circle A is smaller than circle B, then it implies that infinity A is smaller than infinity B. Because imagine, if I have an infinite number of points here, and then I draw from each of those a line, right, that goes out from the center, right, and it crosses over, I superimpose it over that second circle, you're going to see that by the time the two lines on the internal circle make it out here, there's going to be small gaps in between, which looks like the circle A has a smaller set of infinity than circle B. Huh? That doesn't make any sense. And in fact, that's essentially what Isaac Newton thinks. And he just says, well, we're not exactly sure. The infinite might just be beyond the ability for the human mind to comprehend. Well, going back to Georg Cantor, Cantor cannot agree with that. Cantor wants to establish the mathematics of infinity. And he wants to demonstrate but he wants to prove that there really is multiple sets of infinity, right? And so here's an example of, this is famously what's called the diagonal proof, Cantor's diagonal proof. And so let's imagine here that we have a sequence of an infinite series set. So here's set 1, set 2, set 3, and set 4. So set 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, on and on and on. Set 2 is the even numbers, 2, 4, 6, 8, 10, 12, 14, 16, 18, da 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 da. Set 3 here is a 0, 1, 0, 1, 0, 1, 0, 1 pattern that just goes on and on forever. And here's another set. Here's take the odd numbers, 0, 1, 3, 5, 7, 9, 11, 13, on and on. And you can say these are all infinite series, but guess what? If we take the diagonals, we can always, if we take these diagonals, we can always create a new infinite series, right? So that means that there's multiple infinity sets possible, and we can always come up with another one, actually, right? And so the set theory that Cantor establishes is this idea that, okay, each infinity can be regarded as a set of a whole bunch of things. And we can say that if there's a one-to-one correspondence in the infinite, then we have an infinite and we have a well-ordered set. So if two sets merge and they're always the same, it works out pretty well, right? But then there are sets that change and they're slightly different. And so he defined cardinal numbers and ordinal numbers, and ultimately what he calls transfinite numbers, in order to ultimately calculate the mathematical relations between different infinite sets. And then he created a sort of symbolization system in order to ultimately articulate how these sets are related to each other. Now, I know this seems pretty far off. You're probably wondering, how is this related to Frege and categorical logic? I'll get there in just a moment. But I can't say this, is that unfortunately Cantor spent his entire life working on this, and his contemporaries did not like what he had to argue. In fact, his career was sabotaged, and it was hard for him to get published. And his mathematics was actually called a disease by the famous French mathematician Poincare. And then Kronecker actually referred to Cantor as a corrupter of youth, which, if you recall, that's what Socrates was charged with. So it's a sort of striking criticism here, or indictment of Cantor's theory here. But Cantor's theory, and of course it's much more complex than this, we can say that Cantor ultimately sought to establish, whoops, let me go back here. Pardon me. Ultimately sought to establish what he called the continuum hypothesis. That was the idea that there's an infinity of infinite sets. And ultimately to articulate the transfinite relationships between these sets. And ultimately Cantor's unable to do it. And now we know today it's because it's ultimately unstable. And in fact, it's because his set theory includes the possibility of contradiction itself. And ultimately, contradiction, the law of non-contradiction, kicks in here. And it's not just that simple. It's more complicated than this. But ultimately, because of this sort of contradiction created by later Russell's paradox, it actually proves that the continuum hypothesis is not a viable theory. And so today, set theory has been essentially sort of truncated into a sort of kind of minimalist form from the version that Cantor sought to establish. Right? Now, Cantor actually lived a very sad life. And he died sort of a broken man, ultimately, because everyone argued that his mathematics was crazy, and they thought it was just nuts. Now, ironically, without his mathematics, we would not have developed computer science the way we have it today. We would not have developed logic the way we have today. We would not, have NASA wouldn't be flying planes. I mean, we wouldn't have digital technology. The impact of Cantor's set theory is so far-reaching, it's almost difficult to overstate. But ironically, no one really knows his name, and he died penniless and poor and broken, despite having ultimately articulated something that is of such importance that no one could even, in his own day, recognize the implication and importance of what he was doing. And you can always go ahead and take a look at this stuff later. So let's go back to Frege. So what does Frege do? Frege ultimately realizes that, wait a second, he can use set theory in order to combine syllogistic reasoning and propositional reasoning. It's the holy grail. He realizes and he's able to do what no other logician had been able to do yet, right? The same thing that Leibniz wanted to do, the same thing that Boole wanted to do, and so on and so forth, is to realize that the precise relationship, the laws, and articulate the symbolization, a schema, for ultimately relating how quantifiers relate to propositions and concepts. And it's fabulous stuff because ultimately here's the idea is, remember, every category, right, in classical logic, right, if I say all men are mortal, men refers to a category. Well, how many different types of men are there? How many different types of human beings? Virtually an infinite number of types of human beings. And guess what? Mathematics, so the mathematics of set theory, postulates that you can relate sets of infinities to each other, which means that you can actually relate categories to each other, right? And if you're relating these together, what Frege is able to do is basically realize that Cantor's set theory can be employed ultimately to organize the relationships between propositions and their quantifiers. So we might say is that Frege develops the mechanics for combining propositional and syllogistic categorical logic, where each category is treated as a set and each propositional relation gets symbolized. Now here's sort of an example of what Frege's, and this is from the Grundgesetz. But here you see, he actually developed a very bizarre symbolization system that involved drawing lines and having functions and quantifiers, or these sorts of weird Gothic letters. And it's really complicated and it's sort of very difficult to understand. But you can see here that, for instance, like if you're going to do if P then Q, here's how Frege would symbolize it. You have a Q line, and then on top, underneath it is the P line, right? But you can see the Q becomes the central category, and in using the Leibniz's discovery here, you have this idea that P is predicated of Q, right? So Q becomes central, not the subject, right? Here you have, for instance, if you put a line before something, that symbolizes negation for him. Here, if you put a sort of circle, and then you put a sort of half circle, and inside of it you put an X. He used Gothic letters, as you can see. He used F's and G's primarily, and A's. Then what you have is you have a universal statement regarding P, right? You're quantifying P universally, and then of course he has A for the universals. He's got the S for the particulars, and so you end up with sort of statements like this. So, for instance, this is what Frege would have, something like this. And what this was saying is that if this basically says that all A or B, that's essentially what this says, right? Because it says that this X can be anything in the universe. And if it's an A, then guess what? It rests underneath a B, right? Or it is a B. Now, today we would write that just sort of in a very different way. And the symbolization technique that we use today is the one, no one uses Frege's first concept script. And in fact, that's what he called it, the concept script. Now, I won't go through all the sort of mechanics and the brilliance of Frege in terms of his development of logic, but ultimately, he became very famous in terms of developing predicate logic in his own lifetime. He was a sort of renowned logician and philosopher. But ultimately, even while Frege was alive, a number of serious questions begin to emerge whether or not his philosophy ultimately works. and whether or not it's ultimately susceptible to some major problems, which it is. And he publishes two real important essays. One is called Concept and Object. I'm not going to talk about that now, but the other one's called Sense Reference. And we actually have posted a video on the sense reference distinction previously, where we argued that, remember, the sense reference distinction is the idea that we can have multiple senses for a single referent, right? And we can even have senses without a referent, right? So, for instance, if you say the evening star and the morning star, the evening star is one sense, the morning star is another sense, but they both refer to the same thing. That is, they both refer to the planet Venus, right? Or another example, think I've got a son and a daughter who fight a lot, and imagine that my daughter's mad at my son and they come to me and I side with my son or something, right? My son will say, "You are a mean daddy," and my daughter will, no, I'm sorry, my son will say, "You're a good daddy," and my daughter will say, "You are a bad daddy." Well, in that case, good daddy and bad daddy refer to the same referent, me, right? So you can see if you can have multiple senses for a single referent, then that automatically creates problems for the predicate calculus. Because the predicate calculus is meant to articulate the ways in which we quantify and relate our concepts together. But you can see here what happens if we have multiple senses for the same concept, right? What it ultimately seems to show is that it's possible to have, to confuse those senses and therefore not actually trace the logical relation accordingly, or in other words, to come up with false correlations. Now, this ultimately doesn't destroy predicate calculus, but it would be not long after the publication of that article by Frege that ultimately Bertrand Russell here, would publish Russell's paradox. And Russell's paradox ultimately reveals the naive set theory leads to contradiction. And because of that, and because Frege uses set theory, his own project is susceptible to that same problem. Now, what is Russell's paradox? I'm not going to go through, I'll read you what I've put here, and I've just sort of pulled this right off the web here, sort of quick summary of it. But according to naive set theory, any definable collection is a set, and that could be potentially infinite in size. And we can let R be the set of all sets. Pardon me. Let R be the set of all sets that are not members of themselves. All right. So let's say for every set that is not a member of itself, right? Let's make a master set for all of those sets. And the question then becomes, well, wait a second. Then it must be that the definition dictates that it must contain itself, right? Because now we're talking about R is the set of all sets that are not members of itself, right? And if it contains itself, then it contradicts its own definition as the set of all sets that are not members of themselves. This contradiction is Russell's paradox, right? So the idea here is that basically the set of all sets must contain itself, but cannot contain itself. And because of that, remember, set theory is so variable, everything can be a set, and because of the ultimately continuum hypothesis, we should have an infinity of infinities. You can see it doesn't make any sense, right? You're ultimately breaking the law of non-contradiction here. The publication of Russell's paradox here ultimately proved that the naive set theory fails, and that you'd have to truncate or change that theory. And it also demonstrated that Frege's project of predicate calculus would ultimately fail as well. Now, for instance, Russell goes on later to actually publish with Alfred Whitehead what's known as the Principia Mathematica, which essentially sought to do very similar, pretty much the same thing that Russell pretty much did the same thing that Frege was trying to do. Him and Whitehead ultimately created first-order logical proofs for numbers and for the operations of mathematics. But the problem is ultimately another version of Russell's paradox, if you will, ultimately creeps up even for them. And ultimately Kurt Gödel here, he was actually even able to prove, especially with his incompleteness theorem, that even in the logic of the Principia Mathematica, even if that logic is consistent, it's automatically incomplete, right? That is, there is no these projects in terms of determining the final relationships between all of these logical laws and doing it through a sort of logical algebraic system, that project is ultimately always going to be incomplete. And if it's incomplete, it means that it's potentially contradictory. And as a result, you have this severe sort of contraction, or I almost say a sort of sudden realization in modern philosophy and modern logic that this sort of kind of idealism of the sort of Platonic sense of that numbers are objectively certain and in the world and all this sort of stuff. Ultimately, this stuff begins to ultimately crumble. And here's where I want to end our lecture tonight by talking about Ludwig Wittgenstein. I know this lecture has been going on a while, so I appreciate your patience here. But with Ludwig Wittgenstein, we have who was originally actually the protege of Bertrand Russell. And there's sort of two major periods. He's probably my favorite philosopher of the 20th century, probably the most influential as well. And for Wittgenstein, he has two major periods within his course, and he actually even conversed and met with Frege discussing these same issues. The first sort of set of work comes out of his Tractatus Logico-Philosophicus, which is his first major work in philosophy. One of the few works was ever published in his lifetime. But we can say that what the Tractatus's goal is ultimately to articulate what all of the laws of logic are, and he uses a picture theory of meaning and a discussion of logical atomism. I won't go through that. You can go do that research on your own. But ultimately, his guiding interest here is the idea that all of the problems that we do in philosophy occur in language, and all of our language seems to operate under certain logical laws. If we can articulate what those logical laws are, then we'll be able to understand when we err in terms of our philosophical reasoning, right? The idea here is that if you can get the logic straight, you can figure out which problems in philosophy are real problems and which problems are false problems. Ultimately, though, Wittgenstein developed this system, but then he abandoned it, and it changed his view really quite radically in the second sort of major book of his, The Philosophical Investigations. Now, this book wasn't published in his lifetime. It was only published after his death, but it constitutes his sort of his biggest and most important work, I think, in his life. And here, I'm not going to go through, I'm just going to give you a real sort of quick synopsis. I have to say, I always feel bad because and by giving you these quick synopses, I feel like I'm doing irreparable injustice to the philosophical topics themselves, which are much more complicated than what I can say right now. But you can say that in the philosophical investigations, Wittgenstein turns his view really quite radically. Instead of seeing the idea that all of our language is governed by some sort of external set of laws, instead he sees it sort of from not from the top down, from the bottom up, where the idea is that the logic of our language is ultimately based in the Lebensform. Lebensform refers to our forms of life, right? And so the idea here is that our practices are ultimately where the logic of our language is derived from, right? It's not derived from some objective, universal, transcendental reality, right? But rather, the laws of our language are governed by the practices in which they exist. And so that means there is no totality of logic. There is no complete logic. The reason there's no complete logic is because our practices are what's creating the meaningfulness of our language, not the other way around. Our language isn't making our practices meaningful, right? So what you have here is you have in Wittgenstein what we might call a theory of logical grammar that develops, one which is pluralistic in nature. The idea being that there's multiple laws of logic that are governed in certain areas of our discourses. He calls this language games. And the idea there is that when we're using our words, when we use our words, we always use our words in actual context. We don't just use our words in isolation like the philosopher, right, in pure contemplation. We use our words in the middle of daily life. And those words have, depending on the context, those words have meaning or don't have meaning in different ways. So for instance, imagine if I say, well, I don't know, there's so many different examples. Imagine, for instance, if someone says the word sister, right? So if I say, here, welcome, say, let me introduce you to my sister, right? The word sister in that case means what? It means that she's my biological sibling, right? Physiologically, genetically, right? But what happens if someone says, let's say, imagine you're walking in a convent, and someone says, I want to introduce you to Sister Mary Joe or something. Well, their sister doesn't refer to physiological relation. It refers to what? It refers to essentially a nun, right? And someone who's made a vow, a religious vow of some type, right? So in that sense, sister means different things depending on the context, but the idea here is all of our words do, right? Now there's family resemblances between our words, right? So in the context where I say, this is my sister at the restaurant, or if I say, here's Sister Mary Joe at the convent, both of those imply that I have a close relationship to both. That implies that I have a close relationship to both, but not exactly the same. So there's a sort of family resemblance. So you can see here what Wittgenstein's ultimately able to do is to begin to articulate a different conception regarding how language functions and how the meaning of our statements is related. And by the way, this would be a system which avoids the sort of Russell paradox problem. Right? So you have in Wittgenstein this development of a new method. That is, instead of explanation, instead of saying why something is the case, instead begin by describing it, right? So for instance, Wittgenstein says, instead of asking what a word means, let's ask how do we use a word? And we look at the description, we'll ultimately begin to understand is that the logic of our language is rooted to what? These various forms of practices that we employ. Now, there's a little bit more here I want to give you to is that I want to sort of give you an example of how this is related to a philosophical problem, right? For instance, and this comes from a very famous problem in Wittgenstein. It's called the private language argument. But one of the things that's discussed is, for instance, can people have a private language? That is, can people have can people mean things that are purely just subjective and purely personal, right? In principle, right? Ooh, oops, sorry, I just cut myself. And so, for instance, think about pains and pain behavior. So when someone's in pain, they scream and they're like someone grabs their throat and they pretend they're choking. You're going to think that they're in real pain until they say they're not, right? And then you're going to think, oh, you were just an actor or something like this. So the question is, the only way it looks like we know that people are in pain is by their pain behavior. In similar sense, is it the case that we only know what people mean by looking at their word behavior, if you will, right? And so one of the sort of famous examples he gives here is what's called the beetle in the box thought experiment. And here's the idea of imagine everyone when they're born is given is given a box. And everyone is told that you can look in your box, but no one else can ever look no one else can ever look in your box, and you can never look in anyone else's box. But we're going to call whatever is in your box your beetle. So I've got a beetle, you've got a beetle, you've got a beetle. Everyone's got a beetle. I feel like Oprah all of a sudden, right? That was a joke. But the question is, my box, when I look in it, may be empty. Your box, you may look in it and actually see a candy cane. You may look in your box and see a crayon. You may look in your box and actually see a beetle. But all of us are using the word beetle to refer to that thing, right? So the question is, what does the word beetle actually mean? And you can see here, beetle doesn't have a meaning in terms of an ostensive definition. It doesn't refer to something like the morning star refers to Venus. The beetle refers to a certain type of practice. And that's all its meaning is, actually, right? It doesn't have a referent in that sense. And it doesn't have a sense in the same sense either. So you can see here that it has a sense in terms of a living context, right? In terms of a practice. And in the same way he wants to argue, there's a whole series of concepts in philosophy. For instance, concept like the soul, which is like the beetle. Its meaning resides from the logic of the practice, not from some sort of referent, right? And ultimately, Wittgenstein thinks we get into a lot of problems in philosophy because of this. Now, the last thing I'll mention, which is pretty interesting here, is aspect seeing. And he talks about this in the second part of the philosophical investigations. And so taking a look at this sort of photo here, let me ask you, is this a duck or is this a rabbit? Right? Well, if you look at this, it looks like a duck if you see these as the bills. But if you look at this as an eye of the rabbit, and this is the ears of the rabbit, you can see it can be a rabbit or a duck. But notice it can't be a duck and a rabbit at the same time. You either see the picture as a rabbit or you see it as a duck, but not at the same time. And so Wittgenstein begins to think about this idea that it looks like the meaning of the grammar of language seems to be organized by our seeing aspects, where there's certain things that people can say, and we may be blind to understanding what they're seeing. And perhaps our seeing aspects are also correlated to our own forms of life and the own practices that we're accustomed to. But you can see here, Wittgenstein ultimately begins to develop almost a sort of very different type of logic for analyzing philosophical problems, right? And I love this stuff. I find it fabulously interesting to think about, but I know we're running out of time. So let me just conclude with raising one question for you here, which is namely this. And you can see here, I want to make this difference between the world and the mind. And here's my question I want to leave you with tonight, which is, are the laws of logic in the world or are they in the mind? It looks like with the ancient philosophers like Aristotle, the idea was predominantly the idea that logic is in the world. It reveals features about the world itself. Where the modern philosophers seem to be stuck with this question of, is logic in the mind, and if it's not, what is its relationship to the mind? Right? So I think you end up with this division between the mind and the world. And I think you can use that division really to understand the gist and the core problem that we see within the history of the development of logic. Okay? That's a little bit on on philosophical logic and a short brief tour about the history and the development of logic. It's nowhere near conclusive or even sufficient, so I encourage you to continue your analysis and research as you go forward in your studies, but hopefully you can get a sense here that we're actually dealing with some pretty significant philosophical problems in this course, even though our daily sort of routine is just to do exercises and it feels like a math class in terms of calculation. But a lot of things are at stake, namely the fate or our understanding of the mind and the world is what's at stake. Thank you guys for watching, and I'll see you guys online.